Recording in progress.
Okay, I'm going to go share screen. All right, what we're doing today is we're going to finish out Chapter 2. For anyone watching this video online, this is the fall semester of 2022 at College of the Sequoias, and this is Introduction to Statistics, Math 21 for our campus. So the rest of Chapter 2 is on other types of graphs. And graphical misrepresentations. So I think the first thing I want to do is just show you, we're going to start with the stem and leaf plot. And we'll compare it to, say, a histogram. And give you a second to finish writing that. I will blow this up to full screen, my StatCrunch, and we're going to look at, show you one and see what it's doing. And then we'll come back to write. So let me just do the histogram for age again real quick. And let's start at, let's just see what it does on its own. So it bends it every 5 years. That'll work. So that's a histogram for it. And then we're going to do the stem and leaf plot. So what is this doing here? The way the stem and leaf plot works, let me see if I can annotate on my screen. There we go. This value here, the one in the left column, this is called the stem. And it's the first digit. It's a little, that came out pretty good considering I'm using, that didn't. Using a mouse. It's the first digit. So this represents the number 14. This one represents 65. And when we see repeated numbers, like, well, I'll just do this one right here, it means that it occurred more than once. So this means there's a 61 on the list, there's another 61 on the list, and there's a 63 on the list. So notice, like if I kind of turned this table here, if I rotated it like 90 degrees, made it sideways, horizontal, these look like the boxes. There's this box right here. And then we come way down over here. We don't even, the high 79 doesn't show up here, but it's over there. And we got like, this is the 61, 61, 63. So it kind of keeps some of the same properties. It shows areas where there's a high concentration of answers in that range. But notice it's already getting kind of long. Like this line right here is pretty long. And I only have, 180, 200 students on there, or 200 entries on this. If I had 1,000 entries on this line is going to be super long. Whereas this one doesn't. They'll scale the graph to match. So, clear a little bit more, point out some more. So like if I'm reading this, I go to this line. I can see that I've got 3 zeros, so that means there's 3 entries that have a 30 for the age. And then I've got 1, 2, 3, 4, 5, 6, 31, age 31. There's 6 people like that. And that's how this is called the stem and leaf plot. Stop annotating. There we go. Stem and leaf plot. We can tell it to trim stuff. Here it trimmed a lot. It trimmed out anything over 55. That's kind of rude. We can tell it to just trim out things that are really extreme, like the 79. That one's really extreme. So what does this stem and leaf plot have versus the histogram? The stem and leaf plot, it bundles it. We can still bundle the data. Bundles the data. Let me see if I can set my own bins on it. I know I can on that one. I cannot set my own bins though. So when we did it, it decided to bin by 15, the same binning as the histogram in groups of 5. But I can't change it like I can the histogram. The histogram, I can do something like I could start at age 10 and do every 2. So I can edit my histogram's binning. So it bundles the data into bins, which is pretty good. All the while retaining the raw data. I was able to pull out that there was 3 30s right here, but if I look at the histogram, this is the 30 column. I can't identify that there were 3 30-aged people, 3 people aged 30. So the histogram loses the data. It just summarizes it. So the histogram loses the raw data, just gives a summary. Okay. And when the data is continuous, like weight and height, continuous data we can keep all of the, for continuous data, we can keep all the values. We keep that state of being continuous. It's called continuity. Continuity. And the histogram loses it. Histogram turns values into discrete things. We talked about continuous and discrete data like the first lecture. Discrete data made from continuous data. Throws it all into a block. They call doing this process, it's called discretizing. You're not going to need to know these. Continuity and discretizing, discretize. It's not like it's on a test or anything. I'm just sharing some Jeopardy facts for you. Do they still do Jeopardy on TV? I feel like with Netflix and Hulu, I don't even know if. What'd you say, Isabella?
They still have Jeopardy, surprisingly.
Okay, good. So the stem and leaf plots got a lot of good stuff going on. The problem is when you've got too much data. How many rows do I have on my data right now? How many entries are included? 213 rows. If there's any gaps in the age, it'll not have counted those. Nope, I think I deleted all those out. There we go. Good. So 213 rows is starting to get a little jumbly. I mean, there's a lot of 5s, 6s, 7s. It's a little hard. I'd have a hard time counting this many 8s to see how many there was, but I could. If I really needed to know, I could. But that's with 200 people. If I had 1,000 or 1,500, this thing is going to get really, really long. These things are called the leaves. Let's see, annotate. Annotate. There we go. So stem and all of these things over here are called the leaves because they branch off of the stem. It's like a little tree. So it can be pretty handy. The problem lies when there's just too much data. So if there's too much data, the stem and leaf plot is basically unmanageable. It's too big. That was age. Let's take a look at height, how height looks. Graph, stem and leaf plot on height. So people were supposed to report their height in inches. So like 80 means 80 inches tall. That's a big person. That's let's see, 6 feet is 72. So this person, this 80-incher right here is 7 foot, 6'8". 6'8" is pretty tall. Former student of mine. I know who it is. 55 is let's see, 48 would be 4 feet tall. 5 feet tall is 60. So these are under 5 feet tall. But we've got a lot of people in that 5 foot range. 60 up to 72 is 5 foot to 6 foot. There's a lot of people in that range. There's less there. Notice I've got some that say 4.11, 4.11. These people, rather than following the instructions, they wrote, I am 4 foot 11 inches. And the instructions told them how to figure out what it was. Is you take this number, you multiply it by 12, and you get 48. And you add the 11 to it, and you would get 59. So this 4 foot 11 belongs right here in the 59, but it's not listed. So the stem and leaf plot is pointing out that it's an extreme case because someone that's 4 inches tall doesn't make any sense. That's what it's doing right there. Clear. And we've got another type of graph called the dot plot. I am not testing you on stem and leaf or dot plot or any of the stuff we're doing today, other than we're going to cover distribution types, and you'll need to know those. This is all more of a ways you can, when you're wanting to present data, when you're doing stuff, give you some ideas on how to do it. So, the dot plot. So, categories go along the bottom. And we place a dot above each category for each entry. Above the category for each entry. We're going to get to this one through graph and Dotplot. And the one we did before was graph, stem, and leaf. So let's do a dot plot. We see this right here with the low heights. Let's do the dot plot on the height. Let's take a look at that. So what it's doing is for everything in a certain value, it's putting a dot above it. Anything that had a height of 5, or it's rounding to the whole number here, it's putting in this column right here. That's 5 inches. There was people that it says 4 inches because they misentered, and 6 inches because they misentered. Everybody else is down here, and we can see by putting our cursor over what each row has. So 60, there were 4 entries. There were 4 people that were exactly 60 inches tall, or 5 feet tall. This one was a height of, is in the 64 category. People that included their half inch, it's probably me, shit. I'm very proud of that half inch. Anyone that's 64 to 64.99 goes in this column. Notice that it's without this mistaken column over here, that bad column. This is the largest column right here in terms of height. I can't really see how many dots there is though, can I? And I would have a really, really hard time of counting them. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 26, it looks like. This is tedious, right? This would be the same thing would happen with the stem and leaf plot. Oh, let me unhighlight those. Clear. The stem and leaf plot, the 64. Apparently there's 20. That doesn't look like 26 numbers. Well, maybe it is. It gets a little hard to read. And the dot plot's even harder to read because it just puts a dot there. It doesn't show the value. Oh, it's saying up to 2 values per dot. Look at that tricky thing. So maybe that's because I got it small. Yeah, when I make it bigger, it doesn't say that. So if you're making the graph small, now it says, you can barely read it, says up to 5. It's got less dots though. So you can do stuff like that. The bigger you make the graph, the more dots you can show. It's handy when you, where dot plot comes in is when, good for the following. You have a lot of people submitting entries. Results. And rather than sitting there and going, all right, Caprice, give me your 5 numbers and writing them all down, I just you could tell everybody, go up and put a dot above your numbers. So everybody can kind of go do it as once as long as there's room. They can go to a board, whiteboard at school, but Google spreadsheet, online, something like that. And from there, they can place their own data. Now, if you needed to publish stuff like that, this wouldn't work at all. Dotplot is not helpful for a publication or something like that. But it is really handy for getting an idea of responses from people, and everybody's going up and doing them all at once. So ideally, we should do something about all these bad numbers, because these people actually entered responses and they're bad. I can see they're bad. They're bad on this list, on this dot plot. They're bad on the stem and leaf plot. We had all these low numbers. So what you should do, if you have your own data that you're working on, and you know for a fact what they did, how they did it, you should go in and fix it to correct it. People misentered their height. So what I'm going to do is I'm going to come over to height. Nope, that's not what I want to do. I'm going to do data, and I'm going to go to sort. And I'm just, I want to sort all columns, but I want to sort it by height. And now it has all the people in the row. So 4'11" was 59 inches. I'm going to just go through and replace all the 4'11" with 59. Five foot tall is 60 inches. 5'1" is 61. 5'2" is 62. 5'3" is 63. So it's a little tedious, but I can go through and fix the data. Yeah, that was 64. Okay. 65, 66, 66, 67. I don't know if these people entered 5'1" or if they meant 5'10", because this could be misread as 5'1" or 5'10". I don't know what the 5.1s are, because the instructions were to use a 0. And StatCrunch will drop a 0 with the 1 if it's at the end. If I put 5.10 here, it's gonna drop the 0. So I don't know what these are. I would, if I were doing this data set, I would delete these from the heights. And then these I can go on and do. 5'11" is 71. Here I can tell they actually did it wrong. You can't get 5'20", so this had to be a 62. And all of the 6 feet tall people were 72. So I've corrected the data. Now I'm going to go back and look at those plots again. We'll start with the histogram. I missed one. What did I miss? Right there. I missed one. Oop. Okay. So I can do the histogram, and we can look at the stem and leaf. Now it doesn't show any of those low things. There was no 4.11 listed like there was before. But notice how big this has gotten. Now that I've included more of those people in the 5 foot, 6 foot range, these legs have gotten really long. At the size I had it, I couldn't make the screen big enough. And then if we look at the dot plot, stupid zoom window. There we go, dot plot. Height. So now it's the dot plot's doing a little bit better. This is kind of interesting. It like stopped going up a certain height. Is there a reason for that? Why did it do this? It's recording half inches. So 64, two of them were 64.5. So it actually recorded the half, whereas earlier it just stuck all the 64s together. So fixing data is something you can do if you know for sure what the mistake was. You really don't want to tamper with data otherwise. So those are some ideas on graphs. The histogram you'll need to know, but the dot plot and the stem and leaf plot are more for your knowledge rather than something you'll be tested on. And if someone references it, you might be able to remember what it is in the future. Something that's going to come up in the future are distributions. They start in chapter 3, so since today's kind of a short day, I want to cover it here. Let's talk about distributions. It's or how data is distributed. There's 4 main categories. There is the, let's see, there we go. Now I can write it the way I want. There's the first one, which is the most boring, but it does happen. It's called the uniform distribution. This occurs or happens when every outcome is equally likely. I've got some 6-sided dice here. Each side is as equally likely to happen as any other when I roll them. So when you have enough rolls, a dice distribution will usually look something like this. 1, 2, 3, 4, 5, 6. And you've got, like, let's say I did 1,000 rolls. My histogram might look something like this. It's not perfectly flat. Across the top. Let's minimize that. It's not perfectly flat across the top, but it's pretty close. Like I could draw a straight line from left to right, and most of the lines are pretty close to it. That's what we mean by uniform. Uniform in height. On at least on a histogram. So it's got to be things where the outcomes are equally likely. Rolling a die. It looks weird now that they've done this. We'll be doing stuff over there in a second. Rolling a die. Die is singular for dice. I don't want to say dice. Rolling a dice does not have that. Rolling dice has the next one, a bell curve. Drawing suits from a deck of cards. In cards, there are 4 suits: the spade, the club, the heart, and the diamond. These 2 are red. Hearts and diamonds are red. And spades and clubs are black. Okay, so there in a deck of cards, there's 13 of each of those symbols. 13 cards having those symbols for each category. So when I draw from a card from the deck of cards, I have a 1 in 4 chance of getting any particular suit. So those are things that are uniform distribution. The next one that we're going to take a look at is called the bell-shaped distribution. So what's a bell look like? You know, like a bell, you ring the bell. Bell-shaped is referring to this portion right here. A bell-shaped distribution, if I've got the axis, like I've got the 1, 2, 3, 4, 5, 6 axis down there, a bell-shaped distribution does something like this. So this is like a this could be histograms. Histograms can look like this. You're not going to generally see the curve itself, but you will see steep or tall boxes in the middle, short boxes on the end, and it decreases in that shape. This occurs when most data values are near the average. Or mean. Or median. For a bell-shaped distribution, the mean and the median are right in the middle. For a perfect bell-shaped distribution, usually it's just smack dab right in the middle. A lot of things in nature occur this way. We could talk about height. We could talk about weight. We could talk about IQ. In terms of IQ, the IQ test, the mean is 100. A perfectly average person has an IQ of 100, and we'll go over how this works. But people that are above like 145 or below 55 are way out here on the edges, and there's very, very few people in those categories. Most people are within 85 to 115 on the IQ scale. So the mean and the median are kind of the same on the bell-shaped distribution. They're near the middle. Give you guys a chance to finish writing that, and I'll do the next set. Did I smudge that? What happened? You will see the bell-shaped distribution a lot this semester. You'll see the uniform every once in a while, not really all that often. The bell-shaped distribution will be most of our stuff this entire semester. It's so important in statistics that we've learned how to figure out how much is between these two values. Further out, we've got a lot of nice math that goes with it because it happens so often. So the bell-shaped distribution is pretty important. If you need that up longer, let me know. And we've got two more major distributions, and they're the skewed distributions. So let me just draw them. We have our line along the bottom for both of them. So this one here is called the skewed right. Skewed right distribution. And this one is called the skewed left. I personally, it drives me nuts. I get it, I understand it, but I always want to think, when I think right, I want to think, well, where's the hump at? Where's the big amount at? And it doesn't work like that. These sides are called tails. Tail, tail. And when one tail is longer than the other, that's how they describe skewed. So the right tail here is longer than the left tail. So it's called skewed right. On this one, the left tail is longer, so it's called skewed left. So what kind of things happen in these categories? Skewed right. Skewed right happens when there's a lot in the lower end low medium region and only a few that are high. Let me bring this down, center it. I'm doing that one. Few that are high. Perfect example is if Elon Musk were to be in our class and we were talking about income. And I might throw off the distribution as well, being a professor. But if Elon Musk was one of my students and we were doing the average income for students, we would see a distribution without Elon Musk that looks bell-shaped. With Elon Musk in there, he throws it way off. So without Elon, and we're talking about income, most people are in the middle. Some people don't have any income. Some people make more. But with Elon Musk, or pick any really, really, really phenomenally rich person. I don't know what the average income is in Tulare County, but I'm going to say it's under 100,000, probably 40,000, 45,000, maybe a little higher, a little lower. So if we had an average income in the classroom, this is unlikely with a lot of students because a lot of students aren't working. If we had an average income of 45,000 in a room full of 40 students, and Elon Musk walked in with his millions and millions of dollars he makes each year, the average income is going to start showing up as, 700,000. And so the average income with Elon Musk in the room, the mean income with Elon Musk in the room, is so much higher than most people that it becomes useless in terms of using it. So where, like, here is the middle is way over here, but the mean gets shifted to the right. And the bigger this value had, the longer that tail is, the farther right the mean is. This means the mean is larger than the median. Mean is greater than median. We'll talk about this again when we start chapter 3. I will remind you, because that's when we start calculating mean and median, mean or average. So income is a great category for one. Housing prices. Number of children in a family. We have a son with no children. We've got a lot of families that have 1, 2, 3 children. We've got very, very few families that have 9 children. So most families are in this lower region. And it might not even have it might be more, like that for, or more like that for children. Like there's a lot of people with no children. Skewed left goes the opposite way. So the median is still here, middle or median. But now the mean gets shifted over towards the tail, which means the mean is less than the median, which means the average value is lower than most people's value. Data values or data entries. I don't want to say people because it doesn't necessarily mean people. So what kind of things happen in this category? GPA at graduation is something that is in this category. At graduation. So like if you graduate, most people that graduate have above like a 2.5. There are very, very few that are over in the 2.0s or even lower, like 1.8. And I'm going to say most people that graduate are probably above a 3. If you have an average GPA of 2.5, you're averaging B's and C's, you might get tired of being in school going, what is this for? And you may not graduate. So you wouldn't show up on this table. People that have high grades tend to continue and go for it. So that's one example. The next one's a little bit morbid, but it's in this category, age at death. Most people lived in middle age, elder age. Since my mom died recently, I will include her. She got to a good, nice little age over here. Rest in peace, Mom. And most people get to the right side of this graph. Unfortunately, we do have infant deaths. Not many, but I guess 80 probably is closer to over here. But over here would be infant deaths. It's tragic, but they occur. Thankfully, not that often. Most people live to an older age. So those are ideas of different ways that we see. This is skewed left. The tail on the left is longer. Skewed right. The tail on the right is longer. When the tails are about even, we have the bell shape. And when we don't have a hump and it's just like a flat line, that's called uniform. Do you have any questions on that? All right, if you need that up, let me know. I'm going to move it. I'm starting to get a little bit emotional, and I don't want to while I'm teaching. Last thing I want to do is talk about misrepresentation. Misrepresentation in graphs. And I've got some lecture notes that already have the stuff, so I think I'm going to use those. But I'll put this over here as something to write on, as highlight what I'm doing or talking about while I do it. So misrepresenting data. What is that? Why does that have that name there? Huh. Okay, so I'm looking at this data set, and this following time series graph was created from historical data on life expectancy. And what is misleading about it? So if I take the graph and blow it up so it's pretty big, shit, it's not showing up on top. Let's see if I can bring it to the front. In front of text. There we go, it puts it in front. So I'm looking at this data. It's got 1950, 1960, 1970. Every row across the bottom is 10 years. And when I start on 1950, it's really low on the graph, right? It's almost at the bottom of the graph. And over in the 2000, it's almost at the top of the graph. But if we look at the values on the left, this says 68 and this says 78. So what's happening on that graph is in 1950, the average life expectancy was 68. And the year 2000, it's 78. This is a difference of 10 years. Granted, it is a lot. But the difference isn't as big as the graph makes it look. The graph makes it look like a much bigger difference. a much bigger difference. When you just glance on it, you got to read the data, read the numbers on the graph to get anything from it. There is a fix for this. A good way of doing this same graph, because let's be honest, we don't want to have 0s through 68 here, is probably much lower. There's a lot of dead space on the graph. I mean, I could graph it like this. But now I'm making this really tall graph, and a lot of it's just empty space here. Empty or dead space. So that's not desirable either. One way of doing it is doing this. When you have the left side, make a little ripple in the line like that, and then start doing the 68 through the 78 and doing the, the lines. It still shows up pictorially like this picture right here, this big graph right here. But this ripple right here in the axis brings attention to it. Brings attention to. It makes you look. Okay, where is this starting? It's not starting at 0. It's starting at 68. Okay, I can keep that in mind while I'm looking at it. Whereas you may have not looked at the scale and just looked at the height at first. So that's one way of dealing with stuff like that. Click undo. And we can see like 1950 to 1970, 68.2 to 70.8 is only another 2.5 years. It's not a big jump, but it looks like a big jump vertically. It's very short here, and it's almost medium size here. So but it's only 2.5 more years. This jump looks pretty big too. It's only a 3-year jump though. So that's one type of thing you want to look for. Don't do things like that. Another is this 3D pie chart. They look cool, but they are terrible. And I'm going to show you why. Get my annotator thing on right now. See this big wedge right here in the front? This represents the color is 6 to 10. And that's 0.25. This little purple wedge right here is 11 to 15. And it represents 0.23. So we're looking at the tan wedge versus purple wedge. Since the tan wedge is up front, we see more of it. There's a lot more color, a lot of tan on the screen. And a lot less purple. Like if I were to calculate the area of them, I would say purple is half the coloring of the tan, at least, if not smaller. But when we look at the data, 0.25 to 0.23 is not a big difference. if I were to do this on a regular pie chart, that would be my tan and that would be my purple. They look on, and maybe a little bit more. They take up, together they take up almost half the circle. And they look approximately the same size, where purple is just a little smaller. The 3D graph makes purple look very small. This little light blue wedge right here, 26 to 30, right here, is 0.06, which is about 1/4 of the tan. In value. The amount of real estate in the picture is a hell of a lot less than 1/4. 1/4 of the tan picture right here would be doing something like this. Like all this area right here would be 1/4 of the tan picture. And instead we got this little tiny slender wedge. And it's because we're looking at it from the side, so one side shows up better than the rest. So this is why at least the 3D pie charts can be very, very bad. 3D block or bar graphs tend to be better because it doesn't skew it this much. But they can still be a little misleading. But that's pretty huge. Like the area on the screen is phenomenally different. So pay attention when you're looking at graphs or making graphs of your own, that the data that you're seeing is what you think you're seeing. Make sure to read the axes on both sides. If they got the table, skim the results. 68.2 to 77, that's less than 10 years. That's only 9 years. Here, while this looks a shitload bigger than this tiny blue wedge, it's only really 4 times larger. So looking over here can give me stuff like that. So avoid 3 dimensions, avoid distorting data. We don't want a bunch of white space like we have here. So try to make your graphs reflect that. And that will be it for chapter 2. Is there any questions?
I have a quick question.
Yeah.
Whenever it comes to the spreadsheets and showing examples, with like the data about height or weight or whatever it was, are we, like, whenever we're using the website, I can't think of the name right now. StatCrunch. Yeah. StatCrunch. Are we able to kind of do what you're doing?
Yeah, you
or
can.
How is that?
You can do it with your own data, or if you actually want to play around, if you want to play around with this data set, I can, let's see. Let me see if I'm sharing it. I think I am. That's not what I want to do. I want to analyze it. Settings. It is being shared. And so it's called CSI Stats Project Spring 2022. So if you're in StatCrunch, I'm walking through on the screen how to do it. You won't click on My Data. You'll click on Data Sets.
Okay.
And then search by that. CSI, let me find that name of it. CSI Stats Project. And that might be enough. Let's just hit enter. Oh, look. Only one of them comes up. It's me. So, like, if before I searched, it's got all shitload of data on here, data sets that are saved so that other people can access. If you want to check out the one I'm using, yeah, CSI Stats Project.
Okay.
And that way you can toy around with it.
Perfect. Thank you.
Uh-huh. Is there any other questions? If not, we can wrap this up now. We'll call it a day at an hour. If you guys are in the class with the support course, make sure you're working on that. Hansel's perfect timing. He's legendary at showing up when I'm done.
Jesus effing Christ.
Okay. So let me stop recording. I'll give you a quick recap. Let's see.